I'm Ennemcien. So far, we have studied electrostatics, assuming that the medium is free space. We have said nothing about the surrounding medium or its properties. We have just assumed that the surrounding medium is free space. In reality, the charge may be present, the charge may be placed in any medium other than free space. So that we have to generalize the theory. So far, we have used only one electrical constant that is epsilon zero, called the permittivity of free space. Now we have to introduce a new constant which characterizes medium other than free space. Before that, we have to study what are insulator, dielectric material, polarization, dielectric polarization, and so on. So let us begin with polarization, dielectric polarization. Before that, let us see. We have seen that a spherical shell having a charge, electric charge, behaves like a point charge placed at the, as if it were situated at the center of the shell. See, this is a spherical shell with a charge minus q. At a distance smaller from the center of the shell, electric intensity E equals 1 by 4 pi epsilon 0 into q by r square. The same result you will get if minus q, if you place this minus q at the center of the shell. That means a spherical shell is equivalent to a point charge situated at the center of the shell. This is a very important result. Consider a single atom. As you know, an atom consists of a positively charged nucleus surrounded by revolving electrons in various orbits. Of these, the outermost electrons are of utmost importance. They behave like border security force soldiers. They are shielding the nucleus and rest of electrons from outside disturbances. Okay. See, this is a single atom with a nucleus, positive nucleus, surrounded by electrons revolving in different orbits. These electrons are so fast that each orbit behaves like a charged cloud of spherical shape, or a charged spherical shell. Each orbit behaves like a spherical shell with a negative charge, so that the center, it behaves like a point charge situated at its center, that is at this point of the nucleus. Or in short, normally the center of charge of the electron cloud and the nucleus coincide. But you just imagine that an atom, a single atom, is placed in between two metal plates, parallel metal plates with equal and opposite charges, a positive charge and negative charge. There is an uniform electric field directed from positive plate to negative plate, whose intensity is E0. As a result of the electric field, the electrons experience a resultant force towards the positive plate, and the nucleus experiences a force of attraction towards the negative plate. As a result, the electron clouds undergo a shift, or there is a separation occurs between the center of charge of the electron cloud and the nucleus. There is a slight shift introduced between the two. Now this is equivalent to an electric dipole with positive and negative charges separated by a small distance. In short, when you place an atom in an electric field, the center of the electron cloud and the nucleus get separated to a little extent by a little amount, and it behaves like an electric dipole. Or the atom acquires a dipole moment, with the dipole moment directed towards the negative plate, because dipole moment as a vector is directed from minus q to plus q. So here the dipole moment is in this direction, that is parallel to in the direction of the applied electric field. This process is called polarization of the atom. Polarization means the atom acquires a dipole moment in the presence of an electric field.